Okay, this is hour 3 for April 20th for Physics 2016-17. Right now we're going to continue talking about circular motion problems and applications. This problem that we're going to be doing here is a very, very simple problem that is related to a really important idea with circular motion. Okay, and it's called critical speed. So imagine the following. We've got a bucket, okay? And this bucket, let's make it purple. This bucket is right here. And, you know, it's got a handle on it. Here's the top of the bucket. And there's a handle right here. And then this is attached to a string. What I would do if I was in class is I would actually attach this to, like, I would be, you know, we'll just do that way. So you've got a person, and this is their hand, okay? And they're whirling this thing in a circle like this, and it contains water. Okay, so this thing in here is filled with water. And it's being whirled in a circle, and we want to figure out what the critical speed, so a cup filled with water is making a vertical circular motion of radius r. Find the critical speed at the top such that no water is lost. Okay, so all water in here, and then it's going in a circle. And we want to figure out what the velocity needs to be at the top of the motion here such that no water is lost. And really what we're going to be finding here is critical speed, or the minimum speed, such that no water is lost. Okay? So the question makes sense. If you ever want to try this by yourself, what you can do... Okay, I wish I could show you this demo because I think it's pretty neat. And maybe you saw it in one of your other physics classes, but the idea is that you take a bucket. I don't know if you got any buckets at your house. You fill it with water, and you just start whirling it around in a circle, right, where it goes above your head. And what you'll find is that if you whirl it fast enough, the water will never fall out of the the water's never actually going to fall out of that. And one way you could try this for yourself at home if you don't have a bucket is you could take like a water bottle and then take a piece of string and open the water bottle, fill it with water, right? And then attach a string to the water bottle, like near the neck, right? And then you would just whirl that in a circle, and you'd find that the water doesn't fall out either as long as you roll it fast enough. Can you guys visualize what I'm talking about here? Have you ever experienced this before? And if it goes too slow, when it gets to the top, what's going to happen is the water will actually fall out, okay? Obviously, if you take a bucket and you just tilt it upside down, the water's definitely going to fall out of the bucket. But the fact that it's being moved in a circle... you tried it and you failed, Koa. Okay, well, try again, maybe. I've almost failed this before, but it's pretty easy to do. It doesn't take that much speed. So let's figure out what that speed would be, okay? And the circular motion has a radius r, so we are going to have to label on here that the radius r is going to be this radius here. So the person's arm is here, and they're kind of whirling it around, right? It's going around in a circle like that. Oh god, that made it look worse. But the idea is it's going around in a very large circle here. It's not going to be good with a radius r, right? It goes around in a circle. And we call that r. So here's the thing. We want to look at the forces that are acting on the water, okay? Not the forces on the bucket, the forces on the water, okay? What would the forces on this water in here be? Okay, a normal force? I'm gonna say that the normal force here is gonna act down this way. Oh my god, that line is so beautiful. Beautiful and straight. And then there's gonna be a weight too. In what directions is the weight point? Alright, so you've got two downward forces on this water here. You've got weight, and you've got the normal force, right? Gravity, as you say, where the weight is gonna be equal to the mass of all that water multiplied by gravity. Now, I know the water is a fluid, okay, but let's just treat it as one object, okay? It's got its weight, and it's got this normal force, right? Now, if it's moving around in a circle, what's the direction of the acceleration of this system? Is it up or down? Yeah, so our acceleration is going to point this way. Again, a very nice straight line there. And that's going to be our centripetal acceleration. Everything acts in only one direction here, so we can say the net force that acts in what we're going to call the radial direction, which will be this direction, should be equal to the mass of the object times the radial acceleration, which is equal to the centripetal acceleration, which is equal to mv squared over r. There's two forces here. Those forces are the weight, which is W, plus the normal force, and those should be equal to mv squared over r. Right? The weight is mg. And our goal was to find v, right? So let's solve this for v. So we're going to get g times r plus n r over m is equal to g, or is equal to velocity. Can you guys follow that algebra right there? Okay, so let's think about what this says. This says that the velocity of the water is related to, well, there's only one force left over here, right? Which is the normal force, right? The normal force is the only force that remains here. Everything else is some type of constant for the motion. That is to say, you've got the radius here, you've got the radius here, you've got the mass of the object that shows up here, and you've got gravity. The only, let's call it a variable in this case, is n, the normal force, right? What this tells you is that the velocity and the normal force are directly related to each other, right? That means since all the other parameters can't be changed, we assume that they're fixed, right? Like, for example, if I tell you, and I know that sometimes this can be kind of hard to think about, so let's do this. So if I tell you, for example, that the radius of this is like 0.5 meters, and, you know, we say g is equal to 10, what else would we need? That's all we need, right? Then, oh, and the mass. Let's say it's 1 kilogram of water. It's a lot of water, whatever. All of these values are fixed, right? R, G, M, R, right? There's only one thing that's left over, which is the normal force. So what we can say then is that the faster it moves, the bigger the normal force is going to be, right? Does that make sense to you guys? The faster the velocity, the bigger the normal force becomes, right? So what that means is that the faster that you swing this around, and I hope this makes some kind of intuitive sense, the faster that you swing it, just like an amusement park, right? That's exactly right. That's where we're going with all of this. The faster that you swing it, the harder that water gets pushed into the surface, right? And then the surface pushes back just as hard, okay? Just like when you're in an amusement park ride and you go around a loop-the-loop, and the loop-the-loop is designed like this. When you get to the top, the faster you're going, the harder you get pushed into your seat, right? Is that something you guys can all be familiar with? Or is the question what keeps the water inside, or which keeps the water inside? What is it that keeps the water inside? Is that your question, Kenny? Well, but you said which. The word which is forcing me to answer a question that I can't answer. Can you clarify? Are you asking like which force? Like the weight of the normal force? Oh, are you saying because the normal force increases as a result, that thing is, he's agreeing. Yeah, okay. I understand. Yeah, cool. Yeah, it wasn't a question. Good deal. So, the faster the velocity, the bigger the normal force, right? Now our question is, what's the minimum speed? What would the minimum speed be then? Under what condition would you get the minimum speed? Yeah, minimum speed corresponds to the normal force going to 0. It's the only thing that can change. Everything else in here, R and G, are fixed, right? And then so the only thing that can happen to get the minimum speed is to make n 0. So if I want to find V min, I need to make n equal to 0. And that effectively means the water is going to feel kind of weightless for a second, but then we end up getting this relationship that says that the minimum speed is when the velocity, and this is something you need to remember. Well, you don't have to remember it because you could rederive what we just did. That'd be the real way to do it. But this is worth memorizing. This will show up over and over again in these type of problems. When you see that expression minimum speed, when it says minimum speed at the top, you need to be thinking this every single time. Square root RG. you also should be effectively able to prove it by doing this. By, like, it's 3 steps, right? Physics is all about memorizing the least amount of information you need to in order to get what you need. And, like, in this case, you don't necessarily need to memorize this, but I'm just telling you it will show up a lot. You should, at the very least, be able to derive it from first principles. First principles, i.e. Newton's second law. But that's the answer, okay? And we're going to use this to solve another problem here in a second. We're gonna solve a roller coaster problem with this. Anyone have any questions? I'll ask another question. No. That's it. Do you guys have any questions at all? So let's take what we just learned here. Oh, and I want to emphasize that if the velocity of the water is below this speed, the water is going to fall out of the bucket at the top. That's what this means. No water is lost means the water will literally fall out of the bucket if the speed at the top is not at least this value, which in this case you could figure out what that would be. It'd be something like square root of 5 or something like that, right? That's the number. If it's more than that, it's fine. The water will just push harder on the bucket, right? And if it's less than that, the water's going to fall out of the bucket. Okay? So, this is kind of the classical physics problem that we do with this kind of stuff once we know that's true. Suppose that I have a roller coaster, and it's shaped like this. So I've got a big loop-the-loop right here. And let's move this down just a little bit. I've got a loop-the-loop right there. And then I've got a track, okay? And my track is like, oops, I just want to draw. My track is, let's say, like this. This is the roller coaster you're riding on. Okay? And we've got our car riding along this roller coaster. There's our person that's riding inside of it. And let's say that this person is going to ride along this track, they're going to go through our loop-the-loop, and then they're going to come out down here like this. So this is just the track they're riding on, and this is the person. And the question is this. This is, what is the minimum height? Oops. What's the minimum height such that this cart can complete the loop-the-loop without the riders falling out? That's the question. Something related to energy, conservation of energy. Yep, that's what we're gonna have to do here, right? And I'm gonna try to make it clear. I don't want, like, this track is intentionally not straight, okay? It's intentionally not straight because I don't want you to use Newton's laws or other things like that to solve this. All we know is that we need to figure out the minimum speed, or the minimum height, okay? So that if we start from rest, right, so the initial velocity here, v naught, is going to be equal to 0. If that's the case, then what's the minimum height need to be, minimum height, such that the riders do not follow the car at the top. So you're designing this thrill ride. And, if you've ever ridden on a roller coaster like this, you probably know as you ride down the ramp like this, you eventually get to the bottom, right? And once you get to the bottom, you're going to feel, what do you feel when you get down to here, once the car actually gets down to this location here? I would say, I'll just ask, and you guys tell me if this is right or wrong, do you feel yourself, like, push really hard into the track at that point? Yeah, and especially as you make the curves. It's when you make the curves, like as you're riding up this ramp right here, when you get to, for example, like right here, you're going to be pushed really hard into the track at that point, right? But that sensation of being pushed into the track, it starts to decrease, right, as you start to ride up to here, right? Because the normal force, while it points upward here, when you get around to here, it's pointing downwards. And by the time you get to the top, right up here, it should be the case that you feel like you almost fall out of your seat. Is that about right? You guys know what I mean? That once you get to the top right here, it feels like you're almost weightless at the top on certain roller coasters. And it really depends on how it's designed, right? Yes, and it's so fun. Yeah, I agree. It is really fun. So that's what we want to figure out. We want to find the minimum height such that the riders will not fall out of the car at the top of the loop if they start from rest. Okay, but that's going to be the first thing we're going to do. We're going to do one other thing. We're actually going to calculate what happens when I get to this point right here. Okay, so I'm going to call this point C. I'm going to call this point B, and I'm going to call this point A. Actually, that's kind of backwards, isn't it? We'll make them A, B, C. So this will be B. This will be A, and then this will be C. Okay, and we're going to find we're going to calculate a few different things here. We're just going to start with this, and then we're going to find some things about the acceleration of the car at point B, and we'll go from there. Okay. Now, I'll say the following, just to keep you guys on track, and I'm going to have you guys figure this out yourself. We know the velocity at this point now, right? Because if we want to find the minimum height such that the riders do not fall out of the car, what does the velocity at this point have to be? Yeah, exactly. So here's what I want you guys to do. We're going to solve this symbolically, okay? We're going to say the radius of our circle is r, okay? And I want to find h in terms of r, okay? So h is going to end up being something like maybe 7r, or like, 5r, or like, I don't know, 5.5r, right? Okay? That's what your answer is going to be. You understand? So find h in terms of r. You guys got it? I'm going to give you like 5 to 10 minutes, let you figure it out yourselves. This is a pure energy problem. We're not going to worry about friction at all. We're going to say it's frictionless. See if you can find h in terms of r. Okay? Give that a shot. And it is 4:29. I will give you guys, let's say 5 minutes. We'll start at 4:35. So take some time to set it up yourselves. And the other thing I'm going to say is you can save a lot of time by going, you don't have to do the intermediary steps. You can basically say, start from this point, right here, and then go to this point here. You don't need to find anything in between, although you can if you want. We'll come back and do that other stuff later. All right, so 5 minutes. Find h in terms of r. I'm back. Oh, you guys actually have answers now. I think that's the answer. Yeah, 2.5 bar. I think that's right. Yep. You guys 1 more minute. Nope, 4:35. I need seconds on my little thing here. Oh, there's water on my pad. Okay, so let's go through solve this real quickly here. It doesn't take a lot. We're basically saying, our normal, let's use black, work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. There's no springs here, so it's only going to be gravitational potential energy. That's going to end up becoming 1/2 mass times the velocity at point C squared minus the initial velocity, which is 0. And then that's plus mg. And now, since I defined, we're finding this relative to the ground. I'm really sorry. I don't know if that sounded loud or not, but let me turn that down. Was that really loud? I almost always have my ringtone off, but over spring break I turned it back on. So mg, and then it was loud. I apologize for your guys' ears. It's like right next to the mic where my phone is. Now, I'm basically going to say that we call this point down here y equal to 0. Then y sub c, right, would be equal to 2r, because it's r from here up to here, and then another r to here. And, well, h is what we're solving for, right? So y final would be 2r minus y initial, which is this thing h that we're solving for. And then if you solve this, the left-hand side is going to be 0, no non-conservative forces. So we end up getting 0 equals 1/2 mass vc squared is rg, and then plus mg times 2r, and all of this should then be equal to, well, we say minus h equals 0. Is it a negative? Did I make a mistake? This would be y sub c minus y initial. And y sub c would be 2r minus h. Yeah, okay, it looks right. So then we cancel out the m's, and we end up getting that h is equal to, the m's and the g's all cancel out, and you end up getting 2.5r as you guys got. So good job. We're going to do something else with this, but did you guys have any questions about that? It's good to see come back and you guys have actually already solved it. Now, the next thing I want to ask is, I'll just write it like this. Find the radial and tangential acceleration of the car at point B, assuming that it was released from that height. So the idea is that when the car, did I do something to make it act like this? Oh man, I really wish I could figure out what I've done, because this happens so frequently. Well, either way. So here's our car. It's right here. And we want to figure out the acceleration of the car at this point. So we're going to have to say that we do, in order to figure out what its acceleration at this point right here is, I would say that we need to figure out its velocity at that point, first of all. So we can do that by using conservation of energy again. Say work done by non-conservative forces is change in kinetic energy plus change in potential energy. And this is going to be going from 0 over to b. So we'll have 0 equals. Delta k is going to be 1/2 mass times the velocity at point b squared minus 0 plus mg times the y-coordinate of point b is r minus 2.5r. We're starting from the same position that we calculated in the previous part. And so we can use this to find what VB is. So the masses cancel, and we're going to get something like this. VB is going to be equal to, so this would be 1.5r. So I think you're going to get something like this. And I'll let you guys calculate it and see if you get the same thing. That look right to you guys? So the acceleration vectors for this are going to point like this. You're going to have a centripetal acceleration vector that goes this way, and what I would call a tangential acceleration vector, that is to say that points tangent to the surface, that's going to point down like this. Now, to find the centripetal acceleration, we can use this equation here and say that the centripetal acceleration is going to be equal to VB squared divided by the radius r. So in this case, that's going to be equal to, this thing squared is going to be 3rg, so I think you're going to get 3g. That's the centripetal acceleration. And then for the tangential acceleration in this case, I'm going to say, well, the only force that can be acting on this object here, if we think about it, there's really two forces. Oh, look, it worked that time. There's a force that goes this way, right, which is the normal force. And then there's a force that points down this way, which is the weight of the object, right? So if I were to sum forces in the, let's call it tangential direction, those should be equal to m times a tangential. But there's only one force, which is the weight. So the weight is equal to mg, which is equal to m times a tan, which means that the tangential acceleration is equal to a. That's the radial, and that's the tangential. Oh, not a, g. G. There we go. I know for a fact that one of your lab manual problems for, I want to say the third lab manual homework, has a question that's really similar to this, except it involves instead of it just being a cart like this, it involves a ball that's rolling, where that introduces some additional problems that, yeah, you'll see later on. All right, does this make sense to everyone? Anyone have any questions? I see someone typing, so I'm just waiting a second to see if there are questions. No, I don't know. It just happens to be the case at this particular location that acceleration is equal to gravity. I can say that at another point that's not what it would be. So for example, if we chose a different point, like let's say we chose the point that I drew right here, right? At this location, the tangential acceleration would go this way, right? That would be the tangential acceleration. And the radial acceleration would still point back this way, right? Now in this case, I would say that the tangential acceleration is going to be equal to something like g times the sine of an angle, right? Because if you consider an object on a ramp, like just take a box, for example, that's on a ramp, if it slides down the ramp, then the acceleration in the direction along the ramp is always going to be g sine theta, assuming that you've got no other things going on, right? That's it. The fact that it's like basically at this location means it has to be straight down. There's only one force acting on it, which is gravity, so yeah. It tells you also that something about what's happening here, which is that as you're this should be obvious, I guess, but as you're riding up the ramp, gravity's slowing you down, right? So the car has to be moving faster at the bottom, obviously, than it does at the top. Otherwise, it won't actually make it there. I don't know what this is. Clues. So yeah. Okay, if you guys don't have any other questions, we can actually do this last problem. We did this one already. Here, stop it. We did that one. Oh, so there's three more right there. I think we have to do this one. This one is really similar to the one we just did, but we might come back and do that one next time. Yeah, let's do this one. This is kind of a short one. It'll fit right into the last report of class we have here. Okay. So we got a Jeep. It's trying to make a circular turn, and it says find the maximum speed that the Jeep shown can make a circular turn with a radius of 50 feet without tipping over. Assume that the road is level and that there is enough friction. So if you've ever driven in a car that is tall, like an SUV or a Jeep or a Hummer or whatever, just a car that is really tall, the center of gravity of the car tends to be relatively high, which means that there's a potential that the car can tip over if you move too quickly, or roll. They might say the car could roll. And this problem is basically about that. Find the maximum speed that this Jeep shown can make a circular turn. We're going to assume that it's turning to the left. Okay. So we've got our car, and we're going to assume that it's going to be turning to the left, and we want to figure out the maximum speed that it can make the turn without flipping over. All right. Let's draw on the picture here, and I'll make it just a little bit bigger so we can do that a little better. So here's our car. These are the wheels, like basically here. These are the wheels right here and here. And the car is going into the page. It's moving forwards. It's moving away from us. And it's going to be turning to the left like that. Like in the plane of the page. So it'd be like it's going around like in a circle like this. Horizontal circle. And we're looking at it when it's right here. And we want to figure out the forces acting on this car. What are the forces acting on this car going to be? What kind of forces is it going to feel? Normal force? That's going to point up, right? But it's kind of what's the word for it? There's really more than one normal force, right? There's definitely going to be one at this location here. And there's going to be one at this location here. Let's call them like, I don't know, we'll call this one N1. Call this one N2 or something like that. Weight and friction as well, right? So let's draw the weight coming straight down this way. You know, this color, it's really hard to see, so let's use orange, it should show up a little better. Right, so one normal force here. One normal force here. A weight coming down from here. And a friction force. Now, what direction should the friction be if the car's turning to the left? Left, that's right. The acceleration of the car is going to be inwards, right? It needs to make a turn, so it needs to turn left. So that means that the friction force also has to be to the left. And really, there would be two friction forces, right? You'd have one this way. And you'd have one this way. Now, we're looking for the maximum speed, right, to make a turn with this radius, yeah? And it's such that it doesn't tip over. What's going to be happening if the car starts to tip? Is it going to tip to the left or is it going to tip to the right? I'll let you guys think about this. Will it tip left or will it tip right? I kind of want you all to answer. You don't all have to answer, but just like outwards, right? Someone says left. And to be clear, and we have to imagine this in our minds because this is a three-dimensional system. The car is turning left, right? Its inertia tends to carry it off in a straight line, right? So it's going to want to go away from the circle. Now I see, okay, so in terms of the answer, people said, Daniel says left, one other person says left and then right, one person says right, one person says outwards. I think outwards is a good answer, right, left, okay. What I would say is that what's going to happen is the car is going to tend to tip this way. Okay. It's going to tend that way. So, and really it's inertia that makes it do that. You're trying to turn left, your inertia wants to carry you off in the opposite direction, basically, to the right. So the answer is it's going to tend to tip to the right. Okay. Now you guys tell me, what are going to happen to the forces on these wheels if it's moving at its maximum speed? I would say it's going to be riding on one wheel at that point. Right? If it's going to tip to the right, which one of these forces is going to drop to zero? You have the right idea, Ash. I think you got the wrong force. It's N2, yeah. This one, all of these forces basically have to become zero. All of those forces have to go to zero. Because it's going to be kind of riding along on that edge right there when it's right on the verge of tipping. Okay? All right. So, that means if all of these forces go to zero, we are only concerned with the forces over here now, right? So I don't know if I want to like redraw the picture, but it might be worthwhile to do so. So now our situation is like this. The car's going around in a circle where the left wheel has now just come off the ground, and we've got these forces acting. Again, we've got W. Since there's only one of these now, we'll just call this one in, and we'll say the friction force goes back this way. All right. So one of the things we can state about this problem then would be if I define the upward direction to be the y direction and I define the leftward direction to be the radial direction, then we can use Newton's second law, right? We can say, okay, well, I can say net force acting in the y direction in this case should be 0, and the net force acting in the radial direction should be equal to, mv squared over r. And then we can say, okay, well, in the y direction, I've got two forces, right? I've got N and W. In the radial direction, I've just got one, which is the friction force. The normal force N is going to be equal to the weight, but the weight is just equal to mg. And we could say that the friction force should be equal to the coefficient of friction times the normal force. And we don't know what this is, by the way, right? And that should be equal to mv squared over r. And we could replace the mu here. We ended up getting something like mu times mg is equal to mv squared over r. And the m's cancel, and we end up getting something like velocity is equal to the square root of mu times r times g, right? But we weren't given this value. Like, we don't know what mu is. So this isn't going to help us. Like, this isn't given, so this isn't going to help us. We need another equation. Any idea what that other equation might need to be? Yeah, torque. That's right. What would be the condition such that the car doesn't actually tip? What would that mean about the net torque acting on the system? Has to be in equilibrium, right? The car is going to tend to rotate this way, but the weight is going to stop that from happening, right? Net torque equal to 0. This is where these distances come into play now, all right? Now, this is going to look super sloppy on my picture over here, so I might actually draw it on the main picture. In order to define this, you need to pick an axis, right? It just takes you back to the early part of our class, net torque equal to 0. You always have to define an axis. And so what I'm going to pick for the axis is going to be, we'll use blue. You can really pick a couple different points. You could pick the center if you want to. I think a really easy one to pick is this point right here. That's going to be my axis of rotation. Oh, no, it's not. That's a bad one. My bad. Because that eliminates two forces. What's one where I can avoid using the friction force? 1 right here. This point eliminates too many forces, unfortunately. You're left with just one weight to balance. You need to get 2 different things in there. Yeah, we can do center of gravity. That's fine. We'll do this point right here. I was trying to figure out one that I can get rid of only F. I could do it if I pick the midway point in between the two of them. Or I could pick this point here. That would get rid of F. Whatever. Let's use the center of gravity. That's fine. Then we can say that. Let's see. Torque. We need to define, let's say CCW is positive. So we'll have the normal force. What's the lever arm for the normal force going to be? The lever arm is this distance here, right? So 3.6 feet. And then minus F1 multiplied by 3 feet. But then we know that I've kind of dropped these subscripts, haven't I? Oops. Oh, that's considered one stroke. Okay, fine. So we'll just call it N. And there. This equation tells us what the coefficient of friction is actually, right? So this, if we say N times 3.6 feet is going to be equal to F, which is mu times N, times 3 feet. Then we can solve here for mu. The N's cancel, and we're going to end up getting that mu is equal to, ooh, did I make a mistake? Because we're going to get mu that's greater than 1, right? It's technically okay. What's up?
The lever arm for the friction. Oh, yeah, okay.
Well, anyway, we get 3.6 divided by 3, which is going to be 1.2, I think. Mu technically can be greater than 1, and maybe it has to be with the numbers that are in this problem. I don't know. It's kind of why I didn't want it. I wanted to solve this without using mu, and maybe we'll go back and do that in a second. But given that, then if we plug that in here, we'll get the square root of 1.2 times the radius, which is 50 feet. And then if this is in feet, we have to use 32 feet per second squared. And that should be V. Where is... Okay. So if we do 1.2 times... Oh, it's 500 feet, isn't it? Sorry, this is 500. 0, 0. And then... Oh, it is 50. My bad. What'd you get? 43.8? About 44? Other people agree with that? Yeah. Which, as we learned earlier, is about 30 miles an hour. Yeah, sure. Let's talk about the lever arm distances. So if I choose the center of gravity right here to be my rotation axis, then the forces that I'm going to care about in terms of, you know, the torque are going to be the normal force. To find the lever arm for the normal force, it's just this distance here. And again, the way you find that is you basically just extend this line for the normal force up and down as far as you can, and then you find the vertical distance to the perpendicular distance to the center of gravity. So in this case, that's half of this distance here, which is 7.2. Okay? And then, yeah, same thing for the other one. From here, you go down this distance, which is 3 feet. Now, I can do it again, just so that we can do this in a way that avoids using the friction force. I think there's a way to do this. And that would be where you choose the left edge. Let me erase some of this stuff. This stuff is all... Oh, that's not the eraser. Here we go. Let's erase all this stuff. But what if we chose... Let's do that. So what if we chose the left edge? What if we chose this point right here for our axis? Then our equation would look like, let me write this down here. If I do my net torque equation, then we're going to have, I would say, n times 7.2 minus w times 3.6. It doesn't matter, you still have to... I guess this allows you to figure out what the normal force is. Maybe you do have to do it this way. Which we already know. Right, we already knew what the normal force was. So eliminating the friction force doesn't really help us. We actually have to use the torque equation to solve for this, basically. And maybe the better way to do it, what would have been a better way to do it, probably, would have been to just leave this as F. And then solve for F here, right? Whatever. It amounts to doing the same thing, ultimately, I guess, but... There we go. It's 5 o'clock already, wow. Okay, so there's circular motion. I need to stand up. God, sitting here and writing on a little tablet really just... Time flies when you're having physics. Yep, it's true. You know, after a week of not doing this, I will say this is a lot more fun, having a week off and getting back into it. What's up? Yeah, so there's something else, right? From here, right? Yeah. What does that mean? Oh man, I feel like I've confused you guys. For these circular motion problems, will the direction the car is turning be given? Sure. And I mean, if it was turning to the right, we would have done something else too. We would have just drawn our picture different, right? God, I've done this problem so many times, and I'm wondering why. I mean, you need to have this equation for sure to get the velocity in there. I don't know. Okay, I'm going to go ahead and stop recording for now.